Homework was on page 453, 1 to 2, 5 to 9, 11, and 13 to 16. Any issues with any of those questions on page 453? Must be something we need to go over, Kevin. Number 7, okay. Any others? Yep. 15. 7 and 15. Any others? Going once? Going twice? Sold. 7 and 15 it is. 7, my favorite question. My favorite question on the page. One of my favorite questions in the entire book, actually. So it says a Mexican jumping bean moves because an insect larva inside the shell wiggles. Would it increase the motion to have the mass of the insect greater or to have the mass of the shell greater? Who says, show of hands here, who says it would be helpful to have the mass of the insect inside greater? Okay, quite a few people. What about the shell? Okay, couple. Who says doesn't matter, either one? No one? Okay, so most people said the insect larvae. A couple people said the shell, and then there's a few people that just wouldn't commit. Those are the fence sitters, the non-committers, the I don't want to put up my hand in case I'm wrong kind of people. The answer is the insect larvae. So most people were right here. Okay, that's good. Anybody want to explain that? Anybody that said that at least want to explain it? Kevin? No, no. That's a good guess, but it's good. It might have more muscle if it's heavier, but it could just be overweight. Could just be an overweight insect. One of those insects that sits and watches TV all the time, eats potato chips and whatever. So that's not it. Callum? Okay, there could be something to that. It's not the prime reason. Prime reason is related to what we've been doing here with momentum. Yes, yes. Bottom line is the insect larvae is going to transfer the momentum to the shell. If you have an insect larvae that's light in a shell that's heavy, then the insect larvae is going to have a certain amount of momentum to transfer to the heavy shell. A little bit of momentum gets transferred to something that's heavy. What happens to that something that's heavy if only a little bit of momentum was transferred to it? It'll still move, but it will move slowly. If you have something that's heavy inside, then it's going to be the thing with a lot more momentum. Now you're getting more momentum being transferred to the shell that is lighter. So you're going to have now more momentum transferred to something that's lighter, which makes the shell move faster. So instead of transferring less momentum to something that's heavier, you're traveling more or transferring more momentum to something that is lighter. Okay? When you phrase it that way, I think it's pretty clear that the more momentum being transferred to something that's lighter is going to make that shell or that thing that's lighter move faster. So it is definitely the insect larvae needs to be heavier than the shell. All right, the other one we needed gone over was question number 15. Okay, we got a bit of a calculation question here. It says the blue whale is the largest mammal ever to inhabit Earth. Calculate the mass of the female blue whale if, when alarmed, it swims at a velocity of 57 kilometers per hour to the east and has a momentum of 2.15 times 10 to the 6 kilograms meters per second to the east. Everything is east, so probably stands to reason that we'll make east positive. If that's the case, then we're going to say that this is V, and we're going to say that this is P. But as soon as I read through that, I noticed that this is in kilometers per hour. So I want to draw my attention to that, either with a red pen or a highlighter or a star or an arrow or something, so that when I actually go to plug my numbers into my equation, I'm not going to forget to do that conversion. All right, P is equal to M times F, but we're solving for the mass here, so we're going to rearrange that to solve for M. The V goes over by dividing, and I get P over V. P is 2.15 times 10 to the 6. You see how easy it is? At this point, if I hadn't have circled that, I probably would have just put in the 57 there. Okay? You see it, and then you start doing some other stuff like this, and then it's amazing how easy it is just to forget something that you already noticed, unless you've drawn attention to it like I have there. Okay, I shouldn't forget now, because I've drawn attention to it in red. Let's do that conversion here. 57 kilometers per hour is what in meters per second? Who remembers how to do that? Shall we? Yeah, divide by 3.6. And what do I get? 15.8333. Keeps going. We'll go 4 or 5 decimal places until the final answer, right? All right. Let's put that velocity into my equation now. 15.83333. And now we end up getting a mass here. 1.36 times 10 to the 5 kilograms. Thank you, Cassidy, for getting that so quickly. Final answer should be rounded to 3 digits. That's pretty heavy, right? It's a whale. Of course it's going to be heavy. How many people got that? By the way, if you ever want to check your answers to these, the answers don't come right with the questions like they do with our practice problems. They're in the back of the book. Okay, go to the back of the book in one of the appendices and check the answers to the check and reflect questions. They're all there. At least all the math ones are there. Good? All right, we're going to move on today and talk about a concept called impulse. Up until now, very first 3 days of class, we've talked about momentum, and specifically, we said that momentum exists at a particular moment in time. The momentum of an object, how hard it is to stop something, exists now, or now, or now, not over an interval. All those problems we did where the ball was falling from a certain level to the ground, we wanted to find the momentum as it struck the ground, not when it was at the top and when it struck the ground, or not halfway down and 3/4 of the way down, or not over the entire trip down. You can't do that. Momentum exists at one specific moment in time, either at the top or the middle or the bottom or somewhere in between, but not all of them together. Impulse, on the other hand, will account for what happens between the top and the bottom or between the start and the finish. Impulse, we're going to define as the change in momentum between two spots. So your first quiz question, which asked you for the momentum of the ball as it struck the ground, could be rephrased now to say, what's the impulse experienced by the ball as it fell? Momentum at one spot when it struck the ground. Impulse as it fell from the top to the bottom over an interval of time. So clearly it's related to what we've been doing. It's momentum, but it's not specific momentum at one time. It's change in momentum over a period of time. Momentum is a vector, so that means that impulse, the change in momentum, will also be a vector. Now let's go back to the very first stage just for a second here. I said that momentum is how hard it is to stop something. That's the way that we kind of figuratively define momentum, the way that we use to understand momentum, how hard it is to stop something. I asked you a question. I said, what two things make an object hard to stop? What two things contribute to how hard it is to stop something? And you guys answered. Number one, mass, good. The heavier it is, the harder it is to stop. Number two was velocity, good. So mass and velocity make something hard to stop. Mass and velocity contribute to momentum. There are two different quantities that contribute to impulse, or the change in momentum. What two things have to be present if you're going to change the momentum of something? Well, no, not necessarily momentum. Okay? Somebody said, what has to be present? Momentum? No. Okay, this desk, Shelby's desk right now, doesn't have any momentum. Can I change its momentum? Yes. Just did. I imparted impulse to that desk. Not because it had momentum, it didn't have any. It did at the end. I gave it momentum, a change in momentum. But the amount of impulse is not determined by or is not affected by the amount of momentum that it had. Time, good, good. I'll explain that one in a second after I explain the other one that someone's going to give me. What else? Force. Think about that. Okay, this desk right now has zero momentum. If I want to give it momentum, I have to push it. I have to apply a force on it. And I have to apply that force for a certain amount of time. The more force, the bigger the impulse, the bigger the change in momentum I give it. The more time that I apply it for, the bigger the change in momentum. You know that if you push a little wagon just with a little force for 2 seconds, it's going to start moving. You push that wagon with a bigger force, it's going to move faster, more momentum, more impulse. You push it not harder, but for a longer period of time, for 2 minutes instead of 2 seconds, it's going to be going faster, more impulse. So the impulse, the change in momentum, is determined by, or is affected by, both force and time. Now, we're going to derive an equation here that's going to put all that together, but we're going to derive it from something that we've already done before in Physics 20, Newton's second law. Remember that said F is equal to m times a. Rings a bell, right? Remember Newton's first law, an object at rest remains at rest, object in motion stays in motion, so on. Newton's second law said the acceleration is proportional to the force and inversely proportional to the mass. F equals ma. Let's replace A with the simplest equation that we have for A. Instead of m times A, it becomes m times delta V over delta T. Is that okay to do that? To do that substitution? Sure. Now I'm going to rearrange it a little bit. I'm going to take the T up to the other side by multiplying, and I am getting this equation, F times T is equal to m times delta V. Here's another question for you to answer. If m times v is momentum, then m times delta v, the change in velocity, is what? Change in momentum. So m times delta v is equal to delta p. And what's delta p equal to? What do we define delta p as? Impulse. This is the impulse. What was the question that I asked you 2 minutes ago? What were the two things that affected the amount of impulse that was imparted to something? What did you guys answer? Force and time. In fact, force times the time is equal to m times delta v, but it's also equal to the impulse, the change in momentum. Everybody take a look at your data sheets just for 1 second here, okay? Bottom left-hand corner, under energy and momentum, or momentum and energy, I guess it is, you should see F times T is equal to m times delta V. That is your impulse equation. Unfortunately, they don't stick in the delta P like I have here. You have to recognize that yourself. Okay, it's the impulse equation, but it doesn't tell you it's the impulse equation. You just have to remember that. Okay, if you need to set it equal to delta P sometime, go ahead. It's just not there in front of you. Please make a little note on your data sheet right now that that is delta P. That is impulse. F times T is equal to m times delta V. Just to remember it when you're writing a quiz or when you're working on homework. Okay, come test time, you get a brand new data sheet, and it won't say that. But hopefully we'll have done enough questions that you'll just remember it by that time. And that's what it is. Now, we have an equation for this, so clearly we're going to use it sometimes when we have a mathematical problem. When? When do we use it? Well, the most obvious one, I'm not even going to write down. The most obvious one is when a question asks you for the amount of impulse. How much impulse is gained by the car as it whatever? If the question says, what's the impulse, then use impulse to solve the problem and get delta P. But there are two slightly less obvious times when we'll also use this equation to solve a problem. One is when the question talks about a change in momentum. That could be a momentum gain or a momentum loss. Question could say, what was the change in momentum of the ball as it was caught by the catcher? What was the momentum lost by the car as it came to a stop at the stop sign? What was the momentum gained by the ball as it fell towards the ground? If it says change in momentum or gain in momentum or loss in momentum or anything that means that, then let's use this to solve the problem. The other one? When we see a force and a time in the same question. Even if you don't see the word impulse, or for that matter the word momentum at all, if you see a force and you see a time in the question, then this equation, this concept of impulse, is valid. Now, there's lots of other situations that involve impulse. Somebody this morning, when I asked them a question later on, but when we use impulse, said, oh, when a car speeds up, does a car experience impulse when it speeds up? Did its momentum change when it speeds up? Yes. If its speed changed, its momentum changed. But that doesn't mean impulse is a useful technique to use to solve that problem just because there is an impulse. Okay, I'm trying to give you the situations not only in which impulse happens, but in which the mathematics of it becomes useful to solve the problem. So when you have a change in momentum, force and time in the same question, try it. Use this. Okay? Do what you can with it. Okay, I have one example for you today, and that's it. 9.3 on page 458. It says, to improve the safety of motorists, modern cars are built so that the front end crumples upon impact. Okay, believe it or not, we do this. Cars are designed so that they are destroyed in the event of a crash to prevent injury. It's not so that the car manufacturer can sell you a new car because your car is destroyed, although they like to do that. That's not the reason they're designed to be crumpled. It's for safety. We're going to see why in just a moment here. A 1,200 kilogram car is traveling at a constant velocity of 8 meters per second to the east. We're going to call that VI. It hits an immovable wall and comes to a stop in 0.25 seconds. This is going to be time. We haven't been asked a question yet. But if we read between the lines, there is one more given that we're provided here. Can anybody tell me what it is? Good. The final speed is 0. How'd you know that? Good. Hits an immovable wall and comes to a complete stop. Question A says, what's the impulse provided to the car? Clearly, if we're asked for impulse, we're going to use impulse to solve the problem. But let's pretend we weren't. Let's pretend just for a second that we weren't asked to find A, that we went straight to B. How would we know it's impulse now? Good. Good. There's a force and a time. Right? We're asked for the force. We have a time of 0.25 seconds. So we're looking for those key words, right, or those key variables. If we see them, we go with it. Okay, let's solve question A. What's the impulse provided to the car? We know that impulse is equal to F times T, and we know that it's equal to M times delta V. We don't know the force, we do know the time, but without the force, we can't multiply F times T to get impulse. So instead, for question A, we're going to multiply the mass by the change in velocity, Vf minus Vi. What's the impulse? Negative 9.6 times 10 to the 3. What's the negative mean? Give me one of two things. Anybody have one of them? Good. It's a momentum that's lost as opposed to gained. The other thing that you can look at it as, think of it as, is, look, if it was moving to the east, the impulse is to the west. Either thought works there. They both ultimately mean the same thing. Okay, what's the average net force? Let's use the other part of the equation now. Solve for force. Got it by a time of 0.25 seconds. You get a 3.8 times 10 to the 4 newtons. Again, a negative means a force to the west. If it's moving to the east, what kind of force do you have to apply to stop it? To the west, opposite to the direction that it's moving. That's a pretty big force. Let's take a look at question C, which is virtually the same question, but has a different amount of time there. F is still equal to delta P over T. The impulse is still the same. It doesn't matter how the car stops. The impulse experienced by that car will be the same. You're driving down the highway at 100 kilometers per hour. We know right now what the impulse of that car will be. Okay, it doesn't matter. You don't know how you're going to stop. You may come to the gradual stop at a stoplight, or, God forbid, you may crash into a concrete wall. We hope it's the former rather than the latter. We hope you come to a gradual stop at a stop sign. But regardless of whether it's the stop sign or the cement wall, your impulse will be the same. Your change in momentum is going to be the same. So my impulse in question C is exactly the same as it was in B. Negative 9.6 times 10 to the 3 kilograms meters per second. My time now is 0.040 seconds, however. What do we get when we do that math? 2.4 times 10 to the 5? What do you notice about the two forces? One's a lot higher. Which one's higher? The one that took shorter time. Anybody a baseball player here? A couple baseball players? I was in Toronto on the weekend, and I went to 2 Blue Jays games. I was this close to getting a ball. It was literally in my hand. The ball I was behind third base, row 30 behind third base. Foul ball hit. Finally, it's coming, it's coming, it's coming, it's coming. I got it, bounced out of my hand. Literally bounced out of my hand. And this lady in the row in front of me, 2 seats down, bounced softly and gently into her hands. I was kind of panicking because I was all nervous about catching it and whatever, but had I been smart, I would have taken my baseball glove there. That's what I would have done if I had a thought about it. But even if I didn't have my baseball glove, there's something that I could have done to have a better chance at catching that baseball than I did, right? Instead of sticking a hand out, trying to catch it with one hand sticking out like this, right? What do you do? What do you do when you try to catch a ball? Kind of, go ahead. Didn't have a hat on. Good thought. Didn't have a hat on, though. Kind of cradle it a little bit, right? Kind of cradle the ball a little bit. Like when you're catching a ball, if you're a baseball player catching a ball with a glove, you don't just stick out your arm like this and have the ball hit it and try to catch it, right? You cradle it a little bit. You bring it back a little bit. What does that do? It increases the time that it takes to stop. That decreases the force. Makes it like this question, right? Increase the time, decrease the force, which means it's going to hurt your hand less, but it's also going to make it easier to catch, right? Can I get a volunteer here real quick? Donovan? Can you stand up on your desk, please? Can you stand up on your desk? On it? Yeah. Come right up to the top there. Now, Donovan, on the count of 3, I want you to jump off that desk. And I don't want you to bend your knees when you jump, okay? I want you to keep your legs straight. Okay, on the count of 3. No, I'm not going to make you do it. You can sit down. No, you know what? Actually jump, but bend your knees. Do whatever you got to do. Okay, so clearly he bent his knees. Everybody laughed when I said don't bend your knees because everybody knew that that would hurt, right? Even if you don't know why it would hurt, we all have this intuitive grasp that it's going to hurt. Through experience, we all know that when we're jumping and landing, we bend our knees. What happens when you bend your knees? What does that do when you bend your knees? Versus just keeping your legs straight. Kevin? It increases the time, which decreases the force. Donovan's impulse was going to be exactly the same whether he had straight legs or bent legs. The impulse wasn't going to change. But the force on his legs was going to change. The idea is increase the time, decrease the force. Not changing the impulse, just changing the force. Anybody ever been in a car crash here where an airbag has gone off? That's good. I'm glad nobody has been. Airbags are designed so that they inflate so ridiculously fast that they're actually in the process of deflating by the time your head ever hits it. There's holes around the edges of the airbag. There's holes all around the edges. So it inflates really, really quickly by this chemical reaction, this gas that's produced. It's not air, by the way. It's some other gas that's produced. And then that gas is already going out the sides and deflating by the time your head reaches it. Why? Why? Taylor? Shelby? Okay, so what does that have to do with impulse, force, momentum? Yeah, when you hit something softer, it absorbs more, it increases the stopping time. But as it's going away from, this is your head, okay? This is the airbag. Okay, your head is going towards the airbag. It cushions it a bit, probably more than a windshield would, right? But imagine how you're going to cushion it more. This is your head now. This is the airbag. Okay, it's coming towards it. Now the airbag starts going away from it. That makes your head take even longer to stop, right? Even bigger stopping time does what to the force? Decrease it. I mean, that's where you really want to decrease the force, right, is on your head, right? One more quick story, and then I'll let you work on a couple questions here. When I was 8 years old, or around that age, I was out skating out in my yard with a neighbor across the street. My parents live in rural Nova Scotia, and there's this creek that goes beside our property and then behind the property. Nova Scotia, you get snow like crazy compared to here. It's nothing here compared to what it is there. There's times, growing up, there was a handful of times, and I remember getting over 100 centimeters of snow in a storm. That's a lot of snow. But then in Nova Scotia, it doesn't, I mean, that's not very often. That was a handful of times, like maybe 2 or 3 times going up, but still happened a couple times. But then it doesn't stay. Then it'll, a week later it rains and it's all gone. When it rained after a big dump of snow, like 40 or 50 centimeters of snow, my parents' yard, the side yard, would flood. And it wasn't a big deal because it didn't hurt anything. It didn't flood any houses or anything like that. It just flooded this yard. But it gave us, within a day or two, this great rink, because then it would freeze. We'd have this great natural rink that we'd skate on for the next few weeks until we had another melt. I used to play outside there every day and skate out there every day. I remember this one day in particular, it was just me, just 2 of us this one day, me and my neighbor across the street. And I remember I thought, I want to play goalie. I always liked to play goalie, but didn't have any goalie pads. So I had a baseball glove on my hand as a catcher. I had just a hockey glove as a blocker, and I had shin pads on, and skates, of course. My shin pads were my goalie pads, and he was taking shots on me, and I was doing okay, and moving and getting in front of the puck and doing okay, and not hurting myself or whatever. And then at one point, I remember saying to him, Derek was the guy's name. I said, "Go back there and take a slap shot," because I figured, like, I'm not well protected, but if it's coming towards my shins, I'm okay. If it's coming towards my glove, I'll catch it. If it's coming towards my other hand, I'll stop it with my blocker, my hockey glove. And if it's coming towards my face or somewhere not protected, I'll just get out of the way. So he goes up and he winds up a slap shot, and he takes, his kid was 3 years older than I was, so he's 11 or 12, takes a slap shot, and it was, you know, decent. And I kind of go down like this to stop it, and the flap of my shin pad pops out, and that slap shot gets me literally right in this kneecap. It hurt a lot, a lot. This is an 11-year-old taking a slap shot, and it still hurt a lot. There's guys that are taking 100-mile-an-hour slap shots in the NHL and goalies that are standing in front of it. Okay? Sometimes it still hurts. You know, sometimes even when, you know, you've got all that padding, it still hurts. But it hurts a lot less than it hurt me that day when my friend Derek across the street hit me with a slap shot in the knee, even if he was only 11 years old. Why? Why, if you're a goalie, an NHL goalie, or any real goalie, does it not hurt like it does when you're not padded? How does the padding work? Yes. It does a couple things. Okay, that's the one that I want to focus on here. Okay, goalie pads increase the stopping time of the puck. What does that do? Decreases the force. Same impulse, increase stopping time, decrease force. Now the other thing it does is actually takes that force and spreads it out over more area. So it's not just your kneecap that gets it, it's the whole area around your knee that gets it. Right? So a little less force in each area. The big thing that I want to focus on, as I say though, is that increased time, decreased force. Make sense? Okay. Got a couple questions for you to work on here. It's 1:55. And this is pretty much where we're going to leave it here today. So let's see what you can do with these. Just stop me as I'm walking around if you have any questions with them, okay?